Let's start with a really simple question. What is temperature? We talk about it every day. It's hot, it's cold, it's the number on the thermostat. But what if I told you the definition we all learned in school isn't just a little bit off? What if it's fundamentally wrong?
We all learn this one, right? This is the textbook definition, the idea that temperature is just a measure of how fast atoms and molecules are jiggling around. The more they move, the higher their kinetic energy and, the hotter it gets. It sounds simple, it's clean, and it feels right.
Well, here's the thing. When you really start to poke at that simple definition, some pretty big problems start to show up. It turns out this clean, simple idea, it kind of starts to fall apart, and it leads to some really weird paradoxes that have actually puzzled scientists for a long, long time.
So let's start by looking at those cracks in the foundation. We're going to dig into a few simple, real-world examples where the classic kinetic energy theory it just doesn't work. Okay, think about this for a second. You point one of those infrared thermometers at your forehead. It never actually touches you, right? So how in the world could it be measuring how fast the atoms in your skin are vibrating? It can't. So what is it measuring?
What they're actually picking up is the electromagnetic radiation, the infrared light, that your body is constantly giving off. And this right here is our first huge clue. It tells us that temperature is deeply, deeply connected to radiation, not just the motion of particles. Remember that, because it's going to be super important in a few minutes.
All right, here's an even bigger problem. If temperature really is just kinetic energy, we should be able to predict exactly how much energy it takes to heat up a gas by 1 degree. It's a property called specific heat. But when we actually do the experiment, the theory gets it spectacularly wrong.
Now check out this table because it makes the problem so clear. For a simple gas like helium, which is just a single atom, the theory works perfectly. The prediction is dead on. But look what happens when we get to more complex molecules. For water, the theory is suddenly missing about half of the energy. And for something like octane, a big complex molecule, the theory just completely falls apart. It's off by 93%. Where in the world is all of that missing energy going?
And then there's this one, a paradox you've probably seen in your own kitchen. You put a thermometer in a pot of boiling water, and no matter how much you crank up the heat, the temperature stays locked in at 100 degrees Celsius. You are pouring energy into that pot, but the temperature just refuses to change. Why?
Now, the classic explanation is, the energy is just being used to break bonds. But wait a minute. Think about what happens when you break a bond. A molecule gets freed from its rigid structure in a solid, and suddenly it can move around a lot more. Its kinetic energy goes way up. So if temperature is kinetic energy, the temperature should be skyrocketing. The fact that it doesn't is a flat-out contradiction of the theory.
So where did that 93% of missing energy in octane go? And what is really going on when water boils? It's time to follow the trail of evidence.
This is the key insight, right here. What if, when we add heat, the energy isn't just making molecules jiggle faster? What if it's being soaked up into the bonds between the atoms? A great way to think about it is to imagine those bonds are like tiny little springs. You can put energy into a spring by stretching it right. You're storing that energy as tension, not as motion. And that stored tension, that's potential energy.
And here it is. This chart is basically the smoking gun. If you take all that missing energy, the stuff the old theory couldn't explain, and you plot it against the number of bonds in a molecule, you get this, an almost perfectly straight line. I mean, a correlation of 0.98? In science, that is about as close to a perfect relationship as you could ever hope to find. This isn't just a hint, it's screaming at us.
So, here's the crucial takeaway. When we heat something up, a huge chunk of that energy isn't making things move. It's being stored as potential energy, stretching out all those tiny molecular springs. The motion, the kinetic energy, is actually only a small part of the picture.
All right, so with all this evidence, we can now build a new, much better model. It's based on a concept called the dynamic energy triangle, and it brings all these ideas together into one unified theory.
So, in this new way of thinking, the thermal energy inside something isn't just one thing. It's this constant, dynamic dance between 3 different forms. You've got potential energy stored in the bonds, you've got kinetic energy from all the motion, and you've got radiative energy, that infrared light we talked about. Altogether, that's the system's total dynamic energy.
And these 3 forms are always converting into one another. It's a non-stop cycle. Potential energy stored in a bond can be released as a flash of radiation. That radiation can then create kinetic energy.
And kinetic energy from particles bumping into each other can get stored right back as potential energy. It's this constant flow.
So you're probably asking, wait, how does radiation create motion? Well, it happens through this really cool process. When an atom absorbs some of that radiative energy, one of its electrons jumps to a higher orbit. For just a split second, this makes the entire atom puff up, and in doing so, it shoves its neighbors away, setting them in motion. The scientists who came up with this call it transimpact.
Honestly, the best way to picture this is like a microscopic popcorn kernel. A little bit of heat, which is radiative energy, goes in, and then pop. It suddenly expands and shoves everything around it out of the way. That's how one piece of the dynamic energy triangle, radiation, creates another piece, the kinetic energy of motion.
And that brings us to the new definition, the whole point of all this. Temperature is not a measure of kinetic energy. It's a measure of the radiative energy being emitted by a system. And since that radiation comes from the potential energy stored in the system's bonds, temperature is most directly connected to potential energy, not kinetic.
So, now that we have this new theory, let's go back to those old paradoxes we started with and watch how they just dissolve.
Remember thermal expansion? The old theory just said, well, particles vibrate more, so they need more room. Which kinda works, but it completely fails to explain why water famously contracts as it gets closer to freezing. The new theory, though, it says things expand because their bonds are stretching as they soak up potential energy. And this not only explains regular expansion, but it can also handle weird cases like water, where the structure of the bonds changes in a way that overrides the stretching effect.
And what about our pot of boiling water? The new model gives us a beautiful step-by-step answer. First, as you add heat, you're stretching those molecular bonds, increasing the potential energy. But then, at 100 degrees, those bonds hit their absolute limit. They just can't stretch any further, which means the potential energy is maxed out. Since the radiation comes from that potential energy, the radiation level also hits a plateau. And finally, because temperature is a measure of that radiation, the temperature reading stays flat, even as you keep pouring in energy, which now just goes into the kinetic energy of the steam.
You know, this quote from the research paper sums it all up perfectly. Temperature is our window into a system's total dynamic energy. But the part we're actually measuring, what the thermometer is actually seeing, is the glow of radiation coming off all that potential energy stored inside.
And that's where we'll leave it. For over 100 years, we've had this simple, intuitive, but really flawed definition for one of the most basic concepts in all of science. It really makes you wonder, doesn't it? If we could be wrong about something so fundamental for so long, what other truths out there are just waiting for a second look?